The hidden forms of liquids. Unveiling nature's geometric secrets. Do liquids possess a form intrinsic to their nature? Beyond the confines of their containers and the influence of external forces, do they adopt inherent shapes dictated by fundamental physical laws? Socrates, the classical philosopher, employed probing questions to dismantle assumptions and reveal deeper truths. By challenging seemingly straightforward concepts, he illuminated the complexities beneath. Today, we invoke his spirit of inquiry to examine the shapes of liquids, a subject that, at first glance, appears simple, yet unfolds into profound scientific exploration. Let us delve into the hidden geometries that govern liquids when liberated from external constraints, uncovering the elegance and precision of nature's designs. Unraveling common notions. Conventional wisdom draws a clear distinction between solids and liquids. Solids retain a fixed shape, while liquids conform to their containers. However, this dichotomy blurs under rigorous scientific examination. In the late 19th century, French engineer Henri-Édouard Tresca conducted experiments revealing that solids, when subjected to high pressures, exhibit fluid-like behavior. For instance, lead and tin, under compressive forces exceeding their yield strengths, can extrude through apertures, forming continuous streams, a process akin to squeeze casting in metallurgy. This plastic flow demonstrates that the distinction between solid and liquid states is, in part, a matter of degree rather than kind. These findings have significant implications for our understanding of planetary shapes. The Earth's equatorial bulge, or oblateness, is often cited as evidence of a formerly molten state. Yet, the planet's deformation results from the centrifugal effects of rotation and the plasticity of solid rock over geological timescales. Gravitational forces and rotational inertia cause even rigid lithospheric materials to undergo viscous flow, a phenomenon described by Maxwell's viscoelastic model. Hence, the Earth's shape does not necessitate a fluid past but reflects the continuous creep of solid materials under stress. The influence of gravity on form. Gravity is a fundamental force influencing the behavior of matter, from the macroscopic scale of planets to the microscopic interactions within liquids. Consider a hypothetical scenario. On the Sun, with a surface gravity approximately 27.9 times that of Earth, g approximately equals 274 meters per square second, a human body would be subjected to crushing forces far beyond biological tolerance. Conversely, on the Moon, where gravity is about 1/6 of Earth's, g approximately equals 1.62 meters per square second, physical limitations shift dramatically. A viscous liquid, such as maple syrup, would flow more slowly due to reduced gravitational pull, allowing it to maintain shapes unattainable under Earth's gravity. This thought experiment illustrates that in environments with diminished gravity, the intrinsic forces within liquids, cohesion and surface tension, become more pronounced relative to gravitational forces, potentially enabling liquids to exhibit stable forms reflective of their molecular interactions. Plateau's groundbreaking experiments. In the mid-19th century, Belgian physicist Joseph-Antoine Ferdinand Plateau ingeniously isolated the effects of gravity to observe the inherent forms of liquids. Plateau immersed a droplet of oil in a mixture of water and ethanol, carefully adjusted to match the oil's density. According to Archimedes' principle, the buoyant force counterbalances the gravitational force when the fluid densities are equal, effectively nullifying the droplet's weight within the medium. Under these conditions, the oil droplet assumes a perfect sphere, the geometrical shape with the minimal surface area to volume ratio. This configuration results from the isotropic surface tension acting uniformly on the droplet, minimizing the system's free energy. By imparting rotational motion to the suspended droplet using a thin rod, Plateau observed equatorial bulging due to the balance of centrifugal forces and surface tension. At critical angular velocities, quantified by the dimensionless Laplace number and Weber number, the droplet ejects a ring from its equator. This phenomenon qualitatively models the proposed formation of planetary rings and satellites in the Kant-Laplace nebula hypothesis, offering insights into angular momentum distribution in rotating fluid masses. Exploring liquid geometry with soap films. To further investigate the geometric properties of liquids, soap films provide an accessible medium where surface tension effects dominate, and gravitational influences are negligible due to the film's minimal mass and thickness, often less than 1 micrometer. By constructing wireframes in diverse geometries, cubes, tetrahedra, and helicoids, and immersing them in a soap solution, we observe the spontaneous formation of minimal surfaces spanning the frames. These structures are governed by Plateau's laws. Plateau's laws describe the local configuration of soap films. Soap films meet in threes along edges at angles of 120 degrees, satisfying the condition of minimal surface energy. These edges, or plateau borders, converge in fours at vertices at the tetrahedral angle of approximately 109.47 degrees. These soap film configurations physically realize solutions to complex mathematical problems, such as minimal surfaces and harmonic functions. The vibrant colors result from thin film interference, where the optical path difference between reflected light waves causes constructive and destructive interference at varying wavelengths. The principle of least surface area. The observed phenomena exemplify the principle of least surface area, a manifestation of the principle of minimal energy states. Mathematically, this is formulated through the calculus of variations. The soap film shapes correspond to surfaces that minimize the integral of surface area, subject to boundary conditions imposed by the wireframes. Consider the Euler-Lagrange equation, a fundamental equation deriving the conditions for a function to be an extremum of a variational problem. In the context of minimal surfaces, this leads to the minimal surface equation, a nonlinear partial differential equation. These mathematical descriptions underpin the physical configurations of the soap films, revealing the deep connection between physical principles and mathematical formalism. Demonstrations of natural efficiency. Analogous to soap films, elastic membranes can model minimal surfaces. When a rubber sheet is stretched over a frame and subjected to uniform tension, it deforms to minimize surface area while adhering to boundary constraints. In van der Mensbrugge's classic experiment, a loop of thread placed on a soap film retracts into a perfect circle upon puncturing the enclosed film. This phenomenon demonstrates that the circle encloses the maximum area for a given perimeter, a principle derived from the isoperimetric inequality in calculus. Mathematically, for a closed curve of length L enclosing an area A, the inequality states 4 pi A is less than or equal to L squared. Equality holds only for a circle. Here, surface tension forces realign the thread to satisfy this optimal configuration, further illustrating the universality of energy minimization in natural systems. The deeper implications. At the molecular scale, the behaviors we observe arise from intermolecular forces, specifically, van der Waals forces and hydrogen bonding in liquids like water. Molecules within the bulk experience isotropic forces, but surface molecules lack neighboring atoms in one direction, resulting in a net inward force. This imbalance manifests as surface tension, with typical values for water at 20 degrees Celsius being approximately 72.8 millinewton per meter. Systems naturally evolve toward configurations with minimal Gibbs free energy, G, defined as G equals H, Ts, where H is enthalpy, T is temperature, and S is entropy. For liquids, minimizing surface area reduces the system's free energy, as creating new surface requires work against cohesive forces. This principle extends to biological systems. Cell membranes adopt shapes minimizing their surface energy, and in materials science, the grain boundaries in polycrystalline solids evolve to reduce total energy, affecting material properties. Reflections on science and understanding. The exploration from macroscopic observations to microscopic explanations exemplifies the scientific method's power, starting from empirical phenomena and ascending to theoretical frameworks. Socrates' legacy teaches us the importance of questioning assumptions to unveil underlying principles. In physics, this approach leads to the discovery of fundamental laws governing the universe, uniting concepts across scales and disciplines. The intricate dance between mathematics and physics reveals that nature operates on principles of efficiency and optimization, principles that are elegantly simple yet give rise to the complexity we observe. Our journey illustrates that liquids do indeed possess forms inherent to their nature, dictated by the minimization of surface area and governed by intermolecular forces. From Plateau's innovative experiments to the mathematical rigor of minimal surface theory, we uncover a convergence of physics, mathematics, and natural philosophy. By challenging established perceptions and embracing rigorous inquiry, we continue the tradition of intellectual exploration. The intricate geometries and efficiencies observed in liquids are not mere curiosities but windows into the fundamental workings of the natural world. As we advance in science and technology, let us maintain a spirit of curiosity and critical thinking, ever mindful that even the simplest questions can lead to profound discoveries.